So let's continue our discussion on spread spectrum techniques. We have so far understood that in order to tackle or in order to mitigate a hostile channel such as military environment where there could be intentional and unintentional interferences, intentional jamming or intentional interference, or whatever it is. It could be intentional or unintentional. So combinedly, they will impair our transmitted signal. So in order to tackle this, we said a spread spectrum technique will help. And we understood how the spectrum of a signal that is normally to be communicated is spread so that it occupies a large bandwidth compared to the original bandwidth of the message. So in that band, it is made to look like a noisy signal, small signal power, and we have shown that when such a signal is transmitted through jamming environment, at the intended receiver, we said that it can collapse the original signal, whereas the interference signal will be left as it is with a very low strength. And that is how we get a gain. So in the process, we used what is known as a code to spread the spectrum. So that code, we simply assumed that it is also a bit pattern, which will have certain properties, but we did not at that time discuss about the properties of that code, but we just assumed one bit pattern which is repeating at certain rate. So the rate at which this code has to repeat, or the rate at which the code has to be generated, it will all depend upon how much of gain that you require in order to mitigate the interference. So all that we have discussed about the parameters, the processing gain, etc. But it is very important to understand some of the properties of the code that we have used in order to get the advantages that we already discussed in the process of spread spectrum. So first I will describe about the codes, and then later on we will correlate the properties of the code with the objectives of the spread spectrum technique per se. So let us, this code has to satisfy certain parameters. In the literature, if you see, there are many such codes that are invented, and they are reported in the literature. This has been going on maybe for the past 50 years. People have been researching on this, and they have proposed certain method of generating the codes with certain properties. So I would like to explain to you the very simple code known as pseudo random sequence, pseudo noise sequence, PN sequence. Oh, sorry. It is known as PN sequence. It is pseudo noise sequence. So they call this PNS. Okay. This is a sequence of bits. That's why it's called a pseudo noise. Now of the code. It is also called a chip rate. So it is a, we can call it as RC, for example. Okay, RC, chips per second, rate of the code. So this means that we have to generate this code, the ones and zeros, for which you require a shift register, and the shift register has to be operated using a clock, and the clock frequency has to be RC. So let us first try to give a PNS generator circuit and then try to understand. So simple, I assume L to be 7, okay, R can be any value. So you have a small shift register, 3-bit shift register, okay. So you can say it's a feedback shift register. So you have got a shift register, you give a feedback to the input, okay, from here, and these feedback combinations can be anything. There are 3-bit shift register. There are many feedback combinations are possible. I am selecting these two combinations. For example, this third one and the second and third bit are repeated. So what happens is this is the PN sequence generator. Now, for which one clock is required, that is RC. RC is the clock rate. Okay, RC can be any value depending upon what you want to, what is the rate at which you want to generate. It all it depends on the application that you are dealing with. At the moment, let us forget about that and try to understand this. So, how does it work? So normally, when you connect this shift register, and this is exclusive OR gate, so you connect this to the power supply. When you switch on, this shift register can start with any state, because it's a 3-stage shift register. So it can start with all zeros, or 0, 0, 1, or any of the bit pattern it can start with. Now suppose, let us assume that it starts with 0, 0, 1. Starts with 0, 0, 1. Now then, what happens? So initially, when you switch on, let us assume that this first output is 0, second output is 0, third output is 1. Now, when the clock starts, so you have a, let me draw the clock pulse, okay? Like this. This is, let us say, at the rising edge of the clock pulse, the change takes place. It can be a falling edge depending upon whatever shift register you consider. So this is the clock. So initially it started with 0, 0, 1. So initial clock when it started like this. Now our output, we will take output at the third. This is our output. Okay, you can take the output from the third shift register. This is the output of this. This is the output. Let us say output. So initially it was 1. This output would have been 1. Now, when the clock pulse starts here, output will be initially like this. Now, when the next clock pulse starts there, initially it was 1. Okay. Then what will be the next output? So 1 now. Next output will be this one, and this one will get exclusive OR. That is these two. These two are exclusive OR. So it is output is 1. That 1 enters into this, and the previous 0 goes there. So this 0, 0 goes there, and the result 1 like this. Okay. So the next state, initially it was 0, 0, 1. When the next clock pulse comes, because there is an input here, that input is 1. Previously it is 0, 1 and 1. So next class comes, this 1 will be shifted to this output. This output will be shifted to there, and that output will be shifted like that. So shift register works like that, as you all know. So 1, 0, 0. So next is output is 0. So till the next clock pulse it is 0. So this is 1, this is 0. Okay, this is the next class. But now let us see what happens to the next state of the machine. This is called a sequential machine. So this 0 0 is exclusive OR and inputted here, and this 1 will go there, that 0 will come here. So this is the output. So when the next class pulse comes, the state is 0 1 0. So output is still 0, so it will still remain in the 0 only. So 0. Okay. Then what happens in the next state? This 1 0 1. So output becomes 1. When the next state output becomes this output is 1. So 1. Done. Now what will be the next one? 0 1 0. So output is 0 till this clock pulse. Okay, it is 0. Okay. Now what is the next one? 1 0 1. So output is 1. Done. So next is what? 1 1 0. 1 1 0. So that is output is 0. Done up to this. What is next? 1 1 1. Okay. Sorry, I made a mistake here. Sorry. 1 0. This is 1 0 1. Here a mistake. This is the mistake. Yeah, sorry. 1 0 0 1. So here is the mistake. So this 0 1 is 0 1 is 1 and 1 1 and 1 1 1 0. So this afterwards this is actually it was 1 here, now it is 0 like that. 0. Now this is 1 1 1. So output is 1 like this. Then it is 0 1 1. Output is still 1. So it is 1 and 1. Afterwards is 0 0 1. So output will be 1 again. So it will start like that. So you see here. Initially when we switched it on, we assumed that it started with the 0 0 1. So at every clock pulse, the state is going on changing. Up to this, it did. Again, it has come to 0 0 1. So this will go on repeating. So it started with the 0 0 1. Now again 0 0 1. Again the same thing will repeat. So output will be 1 0 0. So this 1 0 0 1 0 1 1. This is one bit, one pattern. This pattern will start repeating again like this as we proceed. Again 1 0 0. So 1 0 0 1 0 1 1. Again 1 0 0 1 0 1 1. So like this pattern will go on repeating as long as you switch it on. So this is one sequence that we have generated using the shift register and the feedback combination. And this has resulted in an output of this type, which is going on repeating like this. Now, such a sequence is used to multiply with the data sequence, as we have shown the other day. We multiply with the data sequence, and then we have shown that we could get spread spectrum by choosing the RC much greater than the data rate. So that is how we got it. Now this sequence is said to be a pseudo-random sequence. Okay, this is a pseudo noise sequence, they call it. Normally, noise means a random phenomenon, a random signal. But for this sequence, they have named it as a noise, pseudo noise sequence, they say. Noise sequence means it is unpredictable, random in nature. So it is not. It will not be a periodic one. But this is a periodic bit pattern. But still, it is called a noise sequence. And also, they have said that it is a pseudo noise. It is not a perfect noise, but pseudo noise. So first, we should understand why they call it as a pseudo noise sequence. And because we need one bit sequence which has got all the properties of the noise-like sequence we want, so that after spreading the spectrum, the spread signal will look like noise. And for the enemy, somebody who is trying to tap your signal will not know whether you have transmitted any signal, or it will only look like a noise for them, because low noise-like signal, and it is a low power signal because you have spread over a large bandwidth, and for them it will look like a noise, so they will ignore it. Okay, and that is how we will hide. We will camouflage our signal and hide behind, and get our signal communication done. So we needed a noise-like sequence. But if you have to generate such a sequence, it is not called noise, it is a deterministic sequence. So a deterministic sequence which can be generated using a shift register like this, which we know completely, about which we know completely. So, but still we would like to call it as a random sequence because it has got all the properties of a noisy sequence. Suppose you had a long random sequence which is not repeating, it will have certain properties. And this kind of sequences have such properties. All the properties of a noise sequence is built into this sequence, and that's why it's called a noise sequence. But it is not a random sequence because it is predictable, it is generatable, so it is not random. So it is called as pseudo. So it is pseudo noise, not exactly noise, but pseudo noise. A sequence which has got all the properties of randomness built into it, but at the same time, it is possible to generate such a sequence. That's why it's called a pseudo. So it's a pseudo noise. This is how the name has been given. Now let us see this small little sequence. How does it provide noise-like properties? So normally, when a noisy sequence means randomly you generate a noise sequence. Simply a noise sequence, if you take, it could be some 1 0 0 1 1 1 1 0 1 1. Some 1 1 1 0 0 1 0, something like that. Randomly it is changing. It will never repeat. A noise sequence will never repeat. It is no repetition. No repetition. But then, if you look at the properties of such a noise sequence, it will have, let us say, one property called balance property. Okay. So property, balance property. So this random sequence will have a balance property. That means if you count the number of ones and number of zeros, on an average, they will be more or less equal. Now, suppose you generate randomly any ones and zeros, say, let us say 1,000 bits if you generate, more or less there will be 500 ones and 500 zeros, but they will be distributed in a random fashion. but there will be 500 ones and 500 or 499 ones and 501 zeros, like that. More or less they are equal number of ones and zeros. Such a property is called balance property. So in the random sequence will have a balance property, will satisfy balance property. And now we can show that this PN sequence that we are dealing with is a small 7 length is 7. In this case, length is equal to 7. Only every 7 it repeats. So length is 7. These 7 bits, if you look at it, this also satisfies this property. So there are, out of 7, there are 4 ones and 3 zeros. Now this length of the sequence can be now changed as a power of 2. So length is always 2 power m minus 1. For example, in this case, we have selected m equal to 3. M equal to 3, therefore L equal to 7. Now if m is 4, then L will be 15. If m is 5, the shift ratio length is 5, then L will be 31. So if the length is 15, then there will be 8 ones and 7 zeros. If length is 31, there will be 16 ones and 15 zeros, like this. So in this sequence, the number of ones and number of zeros are almost equal. Okay, one number of ones is 1 more than the number of zeros, that's all. That means it exactly satisfies the balance property. Balance property means the number of ones and number of zeros should be almost equal. So you take this sequence of large number of ones, random sequence, there is one property it satisfies. This small sequence which is generated by us also satisfies that sequence, so that property. So it satisfies balance property. Therefore, one of the qualifications for it to be called as random sequence is satisfied. Now, second property is run length property. Run length property. Now, if you generate any sequence, if number of ones and number of zeros are equal, it is not that all ones are together and all zeros are together, then number of ones and number of zeros also will be equal. But that is not called random. So ones and zeros have to be randomly generated, randomly placed. So how do you know whether they are randomly placed? How to characterize that quantitatively? Tell these randomly placed. For which there is another property called run length property, which has been told. So what is found is number of runs. Run means, suppose it starts with 1, and how long it can run of 1 with length 3. And next, this is, suppose you start with this run of length 1, run of length 0, run of length 1, run of length 1, length 1, length 1, because here run of ones with length 3. Then again another run of zeros. This is a run of zeros with length 2. Run of 1 with length 1. Run of 0 with length 2. Like that it goes. So if you count these runs, it is found that 1/2 the number of runs are of length 1. So you suppose this sequence. Now I am putting this sequence. Let us assume this sequence 1 0 0 1 0 1. How many runs are there? One is 1, 2, 3, 4, 5. Again, this repeats. Let me. So 1 0 0 1 0 1 1. Next is again 1 0 0. See, afterwards it repeats 1 0 0 1 0 and then goes like that. Okay. So if you look at the runs, take any 7 bits, okay, and then we can calculate the runs. So here it is a run of say starting with we'll start with this. This is one run, 1, 2, 3, 4. There are 4 runs. Again, this 0, 0 repeats here. Okay, because I am just considering this one to be grouped here so that the run can be properly counted. So this is how it looks like. So this is one run, starting with 0, length is 2. Starting with 1, length is 1. Starting with 0, length is 1. Starting with 1, length is 3. So there are, in a 7-bit sequence, there are 4 runs in this. 1, 2, 3, 4 runs. So 4 number of runs. Number of runs equal to 4. Now count length of the runs. This run, first run is length 2. Second run length 1. Third run length 1. Fourth run is length 3. This property says that out of the total number of runs, half of them are of length 1. Now let us see in this sequence whether whether this sequence satisfies this property. There are 4 runs, out of which 2 runs are of length 1. So it satisfies. 2 runs are of length 1. Then it says that 1/4 the number of runs are of length 2. So number of runs are 4. Half of them is half of them having length 1. Length 1. 1/4 of them have got length 2. 1/4 of them have got length 2. Now you see, 1/4 means there are 4 runs. 1/4 is 1 run. 1 run will have length 2. See, out of this 4, this run, 1 run only has got length 2. Okay, so 1/4 the number of runs are of length 2. That is, 1 run will have length 2. Satisfies. And then 1/8. Now it is 1/8 is not relevant here. So if the code length is larger, then there will be the number of runs will be more. So this will be relevant. Like that it goes. 1/8 will have length 3. So in this case, 1/8 is not applicable. So this is how run length property is described. So this random sequence, which is generated by any noisy waveform, will have this run length, will satisfy this run length property. But this small little periodic sequence that we have generated also satisfies this property, run length property. So it satisfies balance property, it satisfies run length property. And there is another important property called correlation property, autocorrelation property. Autocorrelation property, which is very important. So here we simply multiplied. If you look at the sequence that we have generated code and multiplied with this sequence, this signal, if you pass through an autocorrelation, the output of the autocorrelator will show certain type of nature. So if I take the autocorrelation of this sequence separately, what it will show is, with respect to time, if this is the time, okay, and let us say you are starting with the zero time here, and this is chip duration 1 by the TC, 2TC, 3TC, 4, 5, 6, 7. This is the amplitude, let us say, correlation amplitude. So autocorrelation output will look like this. Okay. So this will be same amplitude here. This, let us say, this is 1 and this is 1 by L, which is equal to 1 by 7. Okay. In this case, length of the code is 7, therefore 1 by 7. Minus, this is minus. So if you look at the autocorrelation of this particular code when you generate, here ones are represented as plus 1 and the zeros are represented as minus 1. That is, then only this output will look like this. So with respect to time, the autocorrelation output will look like this. So whenever the code, see the code you are generating and the code enters the autocorrelation register, autocorrelator is like this. For example, it will have one multiplier, it will have one code generator, and then one integrator. Okay, integration. This will be the output. So this code enters here, the spread signal enters here. The receiver will generate one code. It will try to correlate with this. So this will be integrated over a 0 to, let us say, 1 period. It will be say LTC. Okay, so it will go on integrated. When one complete sequence has entered, the output will be continuously available. Starting with the -1, then it will again go on giving you -1. When the complete sequence is entered, then output will be maximum. And here we have assumed that both are synchronized. This is the code generator which is generating the 111010. What is received also is 11001. But they will, see, when this is generating 1, let us assume that we also receive 1 at the input. When this is generating another 1, we assume that it is generating another, the 1. So when exactly it matches, you will find there will be maximum output. But during all other time, you will find if it is not synchronizing properly, it will all the time give you -1. Okay, so this autocorrelator output will be looking like this. And what is the advantage here? Why this property is required? Okay, so when you receive, when if you have transmitted a 1, you will get a positive peak. If you have transmitted a 0, you will get a negative peak, based on which you can detect the bit. At the moment, it will not be that clear, but later on it will be clear. So, based on which you can detect the bits. Another thing is, in the meantime, when there is no peak, in the meantime, this is giving you an output which is 0, almost 0. So, whenever the receiver receives the complete code, it will give you an output. And during other periods, when it is entering into the register, it will give you a 0. So this will help you detecting the signal properly. Now during other times it is -1, so even if there is some interference here, it will not cause any error. Whereas during this period, the signal is enhanced, other period it is suppressed. So this property is going to help at the receiver. In order to detect the signal, this will be useful. Unless, if suppose there is another sequence, any other sequence which is periodic in nature, may not have this type of property. It may have this property. For example, sometimes something like this, like that, like this, like this, like that, like that. Okay. Suppose again this repeats like this. Let us say this is how. So again this pattern, same pattern repeats. Okay. It repeats like this. Suppose this is the autocorrelation of some other sequence. Then this what it will cause is there is no peak available. This peak, normally in this case, what the receiver will do is it will have a threshold like this. If the threshold is, the received signal is more than the threshold, you assume that a bit has been received. If it is less than the threshold, you say bit has not been received. So correctly, when a complete bit enters, sequence enters, it will show you that the sequence has entered. Complete sequence is entered here, again it will show you sequence entered. Whereas here, if you put a threshold like this intermittent value of the autocorrelation will give you a false alarm. So here also it is above threshold, so you assume that signal has been received. But here also it will give you another alarm saying that another bit has come, which is not correct. Whereas your bit length is only this one, so it has to show only at these instances. So these autocorrelation values will not allow you to properly detect the signal. So you require a code to spread the spectrum, to multiply with the data, and that will give an autocorrelation like this, so that you can detect the bits based on the output of the autocorrelator. Output will be clearly a positive value or clearly a negative value depending upon 1 or 0 that you have transmitted. You can easily detect. If this code doesn't have this property, and if the code has got a property, any other property like this, if the code has got this type of property, then it will not allow you to detect the signal easily. So to spread the spectrum, you need a one other bit pattern, but that bit pattern should have certain properties, should satisfy certain properties, so that it will easily allow you to detect the original data that you have transmitted, you multiplied with. So this property is very essential as far as detection is concerned when you transmit a spread signal. So any other code will have autocorrelation values. Here it is all minus. I think one example has been shown. It will be available to you. You can look into that example and find that this is how it will look like. Now, any other sequence will not have this type of autocorrelation function. It will have any random autocorrelation, which will not allow you to easily detect the original signal. So the autocorrelation property is a very, very important property. The signal, the code has to have. So the PN sequence, a very simple, innocent looking this sequence satisfies balance property, satisfies run length property, satisfies autocorrelation property. See, the noise sequence will have an autocorrelation property. Whenever exactly matching, it will give a maximum output. Otherwise, output will be always 0 because it is not repeating. If it repeats, then there will be another output. Whereas autocorrelation value of a noise sequence, as you might have already known, for a noise sequence, autocorrelation will be like this. It will not repeat. It will never repeat. Whereas this is a periodic sequence, therefore this peak is repeating again and again. But it has got the randomness property. So, this innocent looking sequence satisfies all the properties of randomness. And therefore, it will help us to hide behind another signal, help us to show as if it is a noise only, so that the enemy will not understand your signal, and whether the intended receiver will understand that our signal is built into this, and we can easily get back the original signal by passing through an autocorrelator and receive it properly. So this is one important property this sequence has got. One other property called cross correlation property. Cross correlation means between the two. One code with itself is called autocorrelation. When you correlate a code with itself, it's called autocorrelation, whereas the code is correlated with another code. If the correlation between one code and another code is not present, then output will be 0. But if they are strongly correlated, then output will be 1. So if they are partially correlated, so there will be some other output between 0 to and 1. So here in this case, as I was telling you, this kind of the applications of the spread spectrum system, one is an anti-jam system, another it can be in a multiple axis environment. As you might have already known, in satellite communication, for example, satellite is revolving around the Earth, and all the Earth stations are accessing the satellite, they are communicating through the satellite. So the Earth stations, when they are simultaneously communicating through the satellite, they should not interfere with each other. So what they do is, every user will be given a different frequency. If it is a FDMA, a frequency division multiplexer, means every user will be given a different frequency band to transmit. They will not interfere. Similarly, if it is a TDMA, every user will be asked to transmit in certain specified time slots. There is another method called CDMA, code division multiple access. Here, every user will transmit all the time. Every user will be using the same bandwidth, but they will use different codes to spread their spectrum. So in that case also multiple access can be achieved. A lot of advantages compared to the FDMA and FDMA and TDMA, and that is why the CDMA is popular. And this is very popularly used in mobile communication. In cellular mobile communication, as you all know, there is one base station, and many mobiles are communicating with each other through the base station, and there also multiple access is required, and CDMA is one such technique that is used. So in order to use CDMA for a multiple access applications, and if there are many number of users, you require many number of codes with the same property. So I told you to just took an example of this one, a small sequence with length 7. And similarly, if there are many users, you require many number of codes. And all those codes should be such that one will not be interfering with the other. That means what? When you transmit, simultaneously all the codes will be present. One particular intended user would like to receive only one code, but at the time other codes are also present, and how to reject the other codes. So for which the codes themselves should have a cross correlation. They should not have a cross correlation value. That means cross correlation has to be 0, almost 0. So they should not interfere. So you have to generate a set of codes which have all the randomness properties like run length, balance property, run length property, autocomplete property, and at the same time, all of them should have a very, very minimum cross correlation among them, so that it can be used as a multiple axis technique. So that also can be shown. So how do you generate those codes? In this case, in this application, I have considered one shift register, and I considered these two feedback points. There are many types of feedback we can give. So people have studied. This is another research. A lot of research has gone to this field, and how many, if length of the shift register is very large, how many such feedback combinations will result in a sequence which have got all the randomness properties. Now, in this case, length is equal to 7. There are only 2 sequences which are possible. Another sequence is, say, suppose I have a shift register, this is one other sequence. This and this, if you give like this. Previously, we had these 2 output. Now, this and this. If you look at the output here, again I start with 0, 0, 1. It is not necessary that the output has to be always 0, 0, 1. You start with any other output, it will give you the same sequence. Okay, so 0, 0, 1. Now what is the output here? 0, 0. Sorry. So this one, this and this will be exclusive OR. So there will be 1 and the 0, 0 here. Again 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 0, 1, 0, and then 0, 0, 1. So it repeats. This will give you another sequence. This output will be yet another sequence. Previously, you had one type of sequence. Now you have a sequence like this. Okay? Output, if I take 1, 0, 0, 1, 1, 1, 0. Again 1, 0, 0, 1, 1, 0, like that. Whereas the previous one was, you see, 1, 0, 0, 1, 0, 1, 1. Previous was 1, 0, 0, 1, 0, 1, 1. 1, 0, 0, 1, 0, 1, 1. Like this. This is one type of bit pattern. This is another bit. So this is code 1. Code 1. This is code 2, let us say. Code 2. This is also repeating. This is also repeating every 7. So previously we had a feedback combination of the last, second one, third one. Now we are having a feedback combination, first and the third. So it has resulted in the same code. Suppose you are assuming a feedback combination like this. All 3. Okay, let us say all 3 you consider exclusive OR. What will be the output? Again we assume 0, 0, 1. If all the 3, now all the 3 you exclusive OR, what do you do? This is 1, 0, 0. Again 1, 1, 0, 1, sorry, 0, 1, 1. Again 0, 0, 1. You see, it is repeated now. Only four possibilities were there, and again it is repeated. Whereas previously the repetition was, length of repetition is, length of this one L is equal to 2 power m minus 1, maximum length. If you have got 3-bit shift register and m equal to 3, maximum length is 7. So this sequence gives you maximum length 7. This feedback combination also gives you maximum length 7, whereas this feedback combination does not give you maximum length. The output is 1, 0, 0, 1. So again 1, 0, 0, 1. Again 1, 0, 1. So it does not give you maximum length sequence. Maximum length for 3-bit shift register has to be 2 power m 3 minus 1. This is 7. whereas this gives you only 4. And this is not a random sequence. It will not satisfy any of the randomness property. So, like this, there are many feedback combinations. Only 2 feedback combinations resulted in maximal sequences in m equal to 3. When you make m equal to 4, again you try various feedback combinations. There also it is found that there are only 2 sequences. When m is equal to 5, they have shown that there are 6 such possibilities. Like this, if you want more and more number of codes, the length of the shift register has to be increased and appropriate feedback combinations have to be selected in order to get the maximal sequences, and it can be used for multiple access. So for a multiple access application, you require many number of codes which satisfy the randomness properties, and which means it satisfies balance property, run length property, autocorrelation property, and the 4th property I have not mentioned here. So 3rd one, autocorrelation. So 4th property is cross correlation property. Okay. So more and more, if you want to understand, you can open up the book and then try to understand. I will just try to explain to you what is cross correlation. Okay, so the code should have very minimum cross correlation. So autocorrelation should be 2-level autocorrelation. Cross correlation should be 0, almost 0. Now, whether the PN sequences have got 0 correlation, PN sequences do not have 0 correlation, but they have got very reduced cross correlation. And therefore, there are people they have studied a lot of such codes, gold codes, Kasami codes, and then some run length codes. There are so many such codes are invented, which have got different type of cross correlation properties, and so that it can be used for various other applications. And the number of codes that can be generated with a given length of shift register also is a concern. So that is also a design parameter. Now, PN sequence allows you to generate certain number of codes in a given shift register, whereas gold codes allows you to generate more number of codes with a given length of the shift register, with a small compromise on the autocorrelation value, cross correlation value, and so on. So, this is how the code that we use for spreading the spectrum requires to satisfy randomness properties, so that it will allow you to camouflage our signal as a random signal. It will allow you to detect your original data using the autocorrelation property very easily, and it will allow you to apply a multiple access, allow to use in a multiple access environment. So very simple, it will, as it looks, but the applications and the properties that are built into this are really mind-boggling. So this is how, when I took an example of a code, here I just very casually consider one particular code, but the properties this particular code sequence have to satisfy are very significant, have significant value. So spreading the spectrum requires a code. Code requires to satisfy a lot of these properties in order to enable you to communicate in a hostile environment. So this is as far as the code is concerned. So code should have properties like that, and you use it to generate, you spread the spectrum. So first we understood what is spread spectrum, Then we said what are its applications, and then we said how to spread the spectrum. Just took one example like this, where we used a code, and we have understood what should be the properties of the codes that are to be satisfied for this purpose. Now, next would be to understand, is this the only technique to spread the spectrum used in the code, or are there any other methods? So, this is one method of generating the spread signal using this code. And this method is called direct sequence spread spectrum. Similarly, there is a frequency hopping spread spectrum. You will see these techniques of spread spectrum later. So now, so far, I have just tried to explain to you the basic principles of spread spectrum technique. So we will see how this is used as a what are other ways of generating spread signal, and what are the advantages that will accrue because of those techniques. இன்னைக்கு போதுமா? நாளைக்கு வந்து அந்த டைரக்ட் சீக்வன்ஸு அந்த நோட்ஸ் வந்து